And I think mission 3 was going to be collected, when was it? Next Tuesday, right? So, again, any questions about mission 3? Not really? Yeah.
Number 70, where like next to it you said, I think it's may use technology. What do you mean by that? It's like the website that you were just on?
Yeah, exactly, the website I was just on.
Okay. I was just trying to clarify.
Like that, and also to calculate the inverse of a 3 by 3. So like to calculate the inverse of a 3 by 3, because you're supposed to calculate P inverse AP in that problem. So like how do you find the inverse of a 3 by 3 matrix? So yeah, I like this website for finding eigenvectors, eigenvalues. I'll try to make an announcement in this class with the links to these two websites I'm talking about. If you're impatient to make me make that announcement, if you look at the linear algebra website, they're linked there already. But if we go back, this one is pretty nice. Like if we want to calculate, for example, the inverse of a matrix, we don't really care about the row reductions, right? You just want a formula for the inverse sometimes, right? So suppose I want the inverse of, I don't know, 1, 2, 3, 4, 66, 4, minus 1, 0, 0, whatever. Hopefully that's invertible. So it shows you all of the exciting, well, it shows you the end result, which is that the inverse of that horrible matrix I just made up is this. Yay. So that's handy if you're trying to just calculate the inverse of a matrix. On the test, I wouldn't expect you to invert a 3 by 3 matrix by hand. I would expect you to invert a 2 by 2 matrix by hand because we have that wonderful ABCD formula for that case, right? So, other questions? So let's talk about the problem of integral curves then, since we've got a minute here. So another thing to think about, I suppose, is there a series technique for systems? Could we use the series technique for systems? What would that look like? Could we suppose that we had a vector of series and plug it into the differential equation and work out conditions? Could we do that? The answer is yes, you could. But the follow-up question to that is, why would you want to do that? Yes, in principle, those kinds of things could be done, but no one does them in the introductory course because they're just too hideous to think about. The series technique, we content ourselves to look at one differential equation at a time, but really you could think about systems where you had coefficients which were functions of time or whatever. And you could generalize the series technique to systems if you were a glutton for punishment. All right, so remember at the start of the course, we talked a little bit about vector fields. We talked about if you have a vector field F, right? And it could have the form generically P comma Q, right? And I told you guys that if we have a path, let's say R of t, right? And that's equal to dr dt, right? That makes the mapping t maps to R of t what's called a what? This describes, it's a parameterization of an integral curve. All right? It's a parameterization of an integral curve. And so if we furthermore put, R equal to say x comma y, just to give names to the component functions here, then what are we're really up against is what? Like P comma Q equals to what? You know, ddt of x comma y, right? And so when you work that out, of course, what we really are up against is dx dt equals to P and dy dt equals to Q, right? And how did we find, what did we do in test one? I think I had a problem on test one where I asked you to find the, you know, like the Cartesian formula for the integral curve to a vector field. What did we do? How did we solve that? Do you guys remember? I did a trick, right? I did a sneaky thing. I divided, remember I divided dy dt by dx dt and canceled the dt's in order to find dy dx equal to what? I'm like, well, we can find dy dx is equal to dy dt divided by dx dt, right? Which is q over p, right? So before, if we were just wanting to find the Cartesian formulation of the integral curve, we could solve this differential equation. Maybe it's separable even, right? So this wasn't bad. We could do this. Not a big deal. Provided what? Provided that p and q are just functions of x and y, right? Now, so now we can try to solve dx dt equals to p, and we can try to solve dy dt equals to q. And now p is a function of x and y, and q is a function of x and y, right? Can we solve these? Well, I don't know. You guys tell me. If this is equal to, say, x squared minus y squared, and this is equal to x squared plus y squared, have we talked about how to solve these? Versus, let's say, oh, I don't know, 3x plus y, and I don't know, x minus 2y. So the answer is to the first, no, we don't know how to solve those. That's a nonlinear system of differential equations. It's anybody's guess if you could solve that or not, all right? That's beyond the course. See, because I have x squared and y squared, yeah? I may or may not be able to hack my way through this problem. I don't know without trying. On the other hand, if I've got dx dt is 3x plus y, and dy dt is equal to x minus 2y, well, that's a system of linear differential equations. We own those. We can solve all of those. You know how to do it. You just find the characteristic equation, find the eigenvalues, the eigenvectors, write down your general solution. That parameterizes the integral curve to that vector field. But we only can do it, for sure, for vector fields which are made from linear functions of the Cartesian coordinates, okay? I'm kind of scared to even try this one. Yeah? I don't know. We could feed it to Wolfram Alpha, see what it does, you know? Let's do that. I had a student who wanted to have a course in advanced differential equations next semester. Any of you guys interested? I think this course is pretty advanced already. I don't know. X prime is equal to x squared minus y squared. And y prime equal to, what was it? X squared plus y squared. This feels simple enough that it might have a solution. System of nonlinear differential equations. Yeah, Wolfram Alpha's like, that's a no, dog. So this problem is actually a good example of one that we shouldn't try to solve analytically. We should instead use basically a numerical technique to understand. So That's the other thing I still need to talk to you guys about is energy methods, the so-called phase plane analysis, which we shall do. I think that's also coming up like next week. Let me see if I can find it right quick for you guys. This doesn't always work. P-plane. Okay, it's working. Yay! All right, so check this out. We just put x squared minus y squared, and it was x squared plus y squared for the second one. So yeah, I can't solve it, but I can visualize it. I can look at what the direction field for this system of differential equations looks like. This is the so-called phase plane. Let's not put variable length arrows because they're annoying. And there we go. And then if we click, clickety click, it will numerically generate some solutions. So something funny's happening there. Whee! So you can get a sense of what the solutions to this differential equation look like, right? And by the way, those are the integral curves to the vector field x squared minus y squared, comma x squared plus y squared. These are the integral curves. These are the flow lines of such a vector field. If it was a velocity field, that's how the liquid or gas would be tracking in such a case, right? So anyway, I think that's all I got for you guys for today. So have a good weekend. Thank you.